about the electronic structure of atoms. Electronic structure, that means the energy, location, or description for the electrons in atoms. In order to do that, we first need to learn a little bit more about the phenomena of light and properties of waves. And when I say learn a little bit more, I think you've probably heard of some of these ideas, but this will be a refresher for you. And then have a new idea, which I think you haven't heard before, descriptions of energy as being quantized. Now, why are we doing this? Scientists have learned a lot about matter by considering how matter and light interact. That's going to be used to develop this model for what our atoms are like. So before that, we need to learn more about light in this concept of quantized energy. So in section 6.1, let's look at a few properties of light and be able to do conversions between frequency and wavelength using the speed of the light and also the electromagnetic spectrum. So here's some terms that I think you've probably heard before. When I'm talking about a wave, I have this image of the wave going up and down and moving through space. The wavelength, given that symbol lambda, is from one peak position to when that peak position returns again. So if you do the top of the wave to the next top of the wave, that distance is the wavelength. So in this image, the top wavelength is longer than the bottom wavelength. There's a description then when I'm looking at the wavelength here. Wavelength of what when I'm talking about electromagnetic radiation? Electromagnetic radiation has two parts. There's an electric field and a magnetic field, and they're 90 degrees to each other. Both of them are propagating or moving through space at a particular speed. So even though this is shown static, this wave is moving across. Each of the parts are going up and down, up and down. They have a particular wavelength, and they also have a particular frequency for how rapidly they're going up and down, up and down. This equation here describes the speed of the wave. That's one that we are going to want to be able to use. The speed of a wave is equal to the wavelength times its frequency, lambda nu, the product of those. So if we're thinking about light, speed of light in a vacuum travels at 3 times 10 to the 8 meters per second. Meters per second, the meter part refers to the wavelength, and per second, putting frequency in the denominator, inverse seconds are units for frequency. Another thing to add here, the wavelength might be in meters. We also want to be aware of how to do conversions between meters and nanometers. That's something that we're going to do within this chapter, and I'll show you in just a moment. So 1 times 10 to the 9th nanometers, that's our conversion to meters. Why is that useful? Well, look at this example. Calculate the frequency of red light that has a wavelength of 725 nanometers. I would use this equation. I find it helpful to have converted the speed to now nanometers per second because it's being asked in nanometers, and that would allow me to solve for the resulting frequency. Having memorized this conversion between nanometers and meters, good thing to do. Notice that when we're talking about red light, it has an extremely short wavelength, which means the frequency of that wave really high. Pointing out once again, this conversion between meters and nanometers, that's a skill we also want to have. Now, red light has a wavelength around 725 nanometers. We see here the visible region. Yep, the red would be over in this part. You do not have to memorize specific values for different regions, specific wavelength values or specific frequency. Doesn't hurt to know the general values for the visible light region, but it's not required. Notice within here, the visible light, that's just one smaller portion of the entire electromagnetic spectrum. The other regions have different wavelengths, different frequencies. If I look at the ones on the left-hand side, those would be ones with a very high frequency, which means a very short wavelength. And we're going to see that corresponds to a higher energy. Gamma rays, X-rays, very high frequency, very short wavelength. Way over on the other hand, on the right-hand side, something like a radio frequency, that has a really long wavelength. Notice 10 to the third meters. And therefore it has a very small, low frequency to it. And we'll see that also corresponds to a very low energy. So within these, what I need you to do is not memorize specific values, but I need you to be able to put the different regions of the electromagnetic spectrum in order, involving frequency, wavelength, and energy. Moving from a description of light to a description then of quantized energy, this is probably a new phrase for you. What do we mean by quantized energy, and why is it going to be important? Two different experiments we are interested here. Planck and blackbody radiation, and Einstein and the photoelectric effect. So looking then to the textbook, we're in section 6.2, and we're looking at blackbody radiation and the photoelectric effect. And it says, in both cases, they were interpreted as evidence that electromagnetic radiation is quantized. So what do we mean with quantized? So first of all, just the phenomena themselves. Points out that this wave description of light, it does a lot of good, being able to explain a lot of different phenomena involving light, whether it's visible light or infrared or X-rays. But there were some observations that could not be resolved. Other phenomena that treating light with this wave description seemed insufficient. So the different phenomena here are not that bizarre. They're not that difficult to understand. One is simply the emission of light from hot objects. If an object is at a high temperature, tell me about the light that's being emitted. Or what if you take a metal surface and you shine light on it to cause electrons to be ejected? Or what happens if you take a gas and you excite that and you see light being emitted from that? My point being is that when we talk about things like blackbody radiation, photoelectric effect, they might have names that we haven't heard of before, but the phenomena that they're describing are things that I think we can understand. So looking first then at the idea that when an object's temperature goes up, it emits light. The example that they describe here, when solids are heated, they emit radiation, is seen in the red glow of an electric stove burner. That's what I'm trying to show here. If you turn on an electric stove, what happens? Well, it first starts to feel warm, then it feels really warm, then it starts to glow a little bit orange. We're seeing that the light that it is emitting, the electromagnetic radiation, changes. When the temperature of an object changes, it emits electromagnetic radiation of shorter and shorter wavelength, so higher and higher frequency. Let me show you an example of that. So right here on the right-hand side, we see a thermometer. It's showing the temperature of a light bulb, an incandescent light bulb at close to 3,000 degrees Kelvin. What radiation is being emitted from that light bulb? I'm seeing this region next to the red. Next to the red is the infrared. We associate infrared as heat. So that light bulb is emitting heat. It's emitting just a little bit, it looks like, of some red light and some yellow light as well, but it's emitting a lot of heat. That's why an incandescent light bulb is very inefficient. If you have a more efficient LED or some other form of light bulb, it's trying to get away from the fact that an incandescent light bulb, it wastes a lot of energy as heat. Let's see what happens if we change the temperature of the object. So by changing the temperature, we're going to change that profile a little bit. If we start taking it upwards towards the sun, notice that it starts building on the left-hand side. And we can go to an even higher temperature. We can go from the sun all the way to another star, Sirius A, which is close to 10,000 degrees Kelvin. What is being emitted at this temperature? Definitely heat in the form of infrared, all of the colors of the rainbow, all of the visible light, and then over here we get a lot of ultraviolet being emitted as well. But notice as the temperature went up, what happened to the profile? I saw it shifting to the left here. That's what it means when I say that it's emitting shorter and shorter wavelength, so higher and higher frequency. Same shape profile, but I see it progressively grow in intensity and shift over and move from being in the infrared to visible light and then eventually some ultraviolet. Now, why is this important? This particular profile here, easy to measure, but it could not be explained by using classical physics. By classical physics, I mean the physics of the day that had worked from Isaac Newton all the way up to 1900 did not do a good job of explaining this profile. Here I showed the one that we've just been collecting, this dark line. This dashed line right here is what classical physics predicted. It led to what was called the ultraviolet catastrophe. Notice that that line, it's not coming back down. It's just spiking upward. Why is that a big deal? Well, this means that even at room temperature, we would all glow in the dark. Our temperature would be one where we're not just emanating heat of some kind, we're glowing in the dark. In fact, there would be no darkness because we would always have visible light being emitted. In fact, we would have even over here higher and higher energy. Everyday objects would be emitting X-rays, gamma rays. Look around the world. This is not the world we inhabit. So classical physics is really failing miserably on this. The failures right here are not even close. So how are they resolved? They're resolved with a proposal by Max Planck. So he derived this black line. He could theoretically come up with a description that led to the experimental description. But it included this idea that the interaction between matter and energy was quantized. It had to take place in a specific minimum step size. That's what this equation E equals h nu is describing. The energy involves the frequency, we've been looking at that, and then the step size, the smallest increment for, in a sense, the size of that energy. It's a really small number, 6.626 times 10 to the minus 34 joule seconds. But it's still a number. It's saying there is a smallest amount of energy that is involved when we have a transfer between matter and energy. This is how the book describes it. It says that matter and energy can absorb energy only in whole number multiples of h nu, such as 1 h nu, 2, 3, 4. You can't have a fraction. It has to be transferred in these whole number amounts. That's what it means to say that the energy values are quantized. They are restricted to certain quantities. This is said to be a revolutionary proposal. And Planck goes on to win the Nobel Prize for it. Why is this revolutionary? The book uses this example. So let's say we think of an everyday example involving potential energy. If any potential energy value is possible, it would be like a ramp. You've got a continuous range of values. A little bit up, a little bit down. If potential energy was quantized, it could only be at those particular steps. You could be higher or lower, but you had to be on one of the steps. Now, what if we really experience potential energy as quantized in our everyday world? I think the finding is more radical than these pictures suggest. Because that would mean that you could be on one step and have a potential energy. You could be on another step, but you could never be in between the steps. You had to have one of those quantized energy values. You couldn't be in between. So to say this is revolutionary, look at what this is saying. You can be on one step or the next or the next. You can be moving from one step to the other step, but in that moving, you are never in between. This is a bizarre idea. How can you be on one value or another value and another value, but never found in between? This is what it means to say the energy is quantized. Now, this is a crazy idea. In chapter 6, we're going to have a lot of crazy ideas. I need more support. I get more support from this experiment involving the photoelectric effect. So following Planck is Einstein. So he's aware of Planck's work, and he's trying to explain this phenomena. You've got light shining on a metal surface, and electrons are being ejected. Here's a picture of it. I like this description here to show me a little bit more. So I have light that's going to be shining on a metal surface. If electrons are ejected, they're going to be pulled across here and move left to right. In this simulation, I can change things like the intensity of the light, its wavelength, and I can change the metal surface. So let's explore that. So I'm going to turn on the light. Intensity goes up as the light gets brighter, and I see electrons being ejected. If I change the color, I'm going to make it go towards green, yellow, red. Wavelength is getting longer. You notice that they stopped being ejected. It's only at the shorter wavelength where they're being ejected. I mean, I can change the brightness of it. They're still being ejected. If I go way down, I guess I could make it quite dim. I still see them being ejected. The crucial variable describing whether they will be ejected or not seems to be the frequency. And if I go to a longer wavelength, which means a smaller frequency, they're not being ejected anymore. What if we change the surface? I'm going to change it to copper. I don't see any being ejected. If I take it towards red, I don't see any being ejected. What if I shorten the wavelength? Shorter, shorter. Okay, so for copper, I have to have a much shorter wavelength compared to sodium. Now they're being ejected once again. So the metal itself also seems to be important. What if I change to platinum? Even if I make it a bright light, I got nothing being ejected. I'll go, first of all, to a longer wavelength. I would say, as expected, now I'm not seeing anything ejected. What if I go shorter? Shorter than copper? Okay, they're being ejected once again. So within this description right here, we're shining the light onto a metal surface. Initially, I'm showing here a red light being shown. I'm going to start to lower the wavelength, which means increase the frequency. Nothing. Okay, now I've reached a value that will allow the electrons to be ejected. If I continue on and make it shorter, yep, they're still being ejected. Crucially, it is the frequency of the light that is telling me whether the electron will be ejected or not. Different metals have different amounts of energy necessary to remove an electron. The frequency of the light seemed to be crucial. It must be above this threshold frequency. It must be above the value for the particular metal. If the frequency was too small, no electrons were being ejected. It needed to be above this threshold value, which we call the work function. The work function is then a characteristic of the metal itself. The way that Einstein interprets this is he says that the light, it's acting like a particle. Light as a particle, we call a photon. The energy of each photon, he goes back to Planck's description. The energy of the photon of light is E equals h nu. This is the energy now that we can think of for a particle of light. So to replace that, instead of showing just this color, now let's try to redo that and show that it's particles of light. And those are what are striking the surface and causing the electrons to be ejected. So why is this novel? Well, there's other experiments that indicate that light acts as a wave. You've probably heard the phrase of a light wave. Diffraction is one such example. This is showing that, at least in this experiment, light is behaving like a particle. This is going to be an important idea for us in Chapter 6. Now, how do I want you to understand this? I want you to understand the different aspects of the experiment and what they mean in terms of then the response within the experiment. When I think about the description of the light, the frequency of the light was crucially important. Its energy was described as E equals h nu. That was for a particle of light. I could talk about the wavelength of that light because I can do conversions using C equals lambda nu as well. So I need you to understand that the light, the frequency was crucially important. It needed to be above this threshold value. And it needed to be, if it wasn't being ejected, you needed a higher frequency, which meant a shorter wavelength. The brightness of the light, that's the intensity of it. Turns out that's how many photons of light I am delivering. More photons, brighter light, higher intensity. In each of these cases, one photon is going to interact with one electron. We're not dividing it up, remember? E equals h nu tells me I can't divide up that energy smaller. I can transfer it to an electron, but I can't like cut it in half in some ways. When it comes to the metals, well, we've seen that different metals have what we'd call different work functions. In some cases, it's easy to remove an electron. Other cases, it's more difficult. It's easy to remove an electron for something like sodium. It's very difficult, as we saw within the simulation for platinum. Gold would be another example. Difficult. Those would have higher work functions. Now, what happens if the photon coming in, if that energy is greater than the work function? I think it's going to emit, it causes an electron to be ejected. Now, if it has extra energy above that threshold value, it's going to add kinetic energy to that electron. It'll give it a boost. It'll make it move across even faster. If you noticed within that simulation, some of the electrons that were ejected were moving fast and other ones slow. That tells me in the metal, different electrons are held tightly to different degrees. So it's possible then to eject an electron and give it an extra boost if the photon coming in has extra energy. Those are different aspects of the phenomena itself. Now, why are we talking about the photoelectric effect? Why is it important? We're going to use this idea a lot within the chapter. We will definitely be using this idea of E equals h nu because we're going to be interested in the energy of these particles of light. This idea of a photon interacts with an electron, we are going to use that to study and learn more about the electronic structure of the atom, where the electrons are found and their energy levels. And this idea of light can come in as a photon and remove an electron, that's going to be a really important idea for us as well. We've seen how different metals become cations, they lose electrons. The energy involving removing an electron, really important idea for us. So we see that within this photoelectric effect, a lot of important concepts. Let me share with you a calculation that we typically would do. If we know the wavelength of the light, well, we could calculate the frequency. We could go back and forth within that relationship. And if we have the frequency, we could calculate its energy. My point being, we want to be able to use both of these equations, E equals h nu and C equals lambda nu. So this question, what's the energy for one photon of ultraviolet light if we know its wavelength? This would be my setup. I want to get to E equals h nu. So E equals h nu, I've got Planck's constant. How do I get to the frequency? I'm going to convert between the wavelength, get to the frequency by using the speed of light. That's what I'm doing within this term right here. I'm going back and forth using both of these equations. This will tell me then the photon, the energy for one photon, for one particle. It's a really small amount of energy. Another way that we see this expressed is not the energy just for one particle, but for a mole's worth. And when we look at it in a mole amount, it oftentimes then is in kilojoules. So using this equation, I've calculated the energy for one photon of light. What if instead of 1, I had Avogadro's number, 6.02 times 10 to the 23rd? And instead of being in joules, I was in kilojoules. So here I show with dimensional analysis and converting that to kilojoules per mole. Important ideas are things that you're going to be asked to do on this screen. You'll definitely be asked to do calculations using both of these equations. You'll be asked to recognize that when you do that, that is telling you the energy for just one photon. So doing a conversion and expressing it in kilojoules per mole of photons, commonly done. So coming back to this idea right here, we're going to explore more how this idea of quantized energy is really important as we develop models then of our atoms. I'm going to leave you with a couple questions to see if you want to begin to apply this. So this is question 6.30 from the end of the book. If you want to get a head start on that, that's one that I'm going to discuss in class. Other ones that are relevant I give here. One involving the electromagnetic spectrum in terms of putting them in order, looking at specifics, and then doing calculations, converting between the speed of light, wavelength, and frequency, all good skills to practice.